so just an overview of activity, independent samples, confidence intervals, CI. Teacher believes there may be a significant difference between how a student performs on an algebra test and a geometry test. Right, so those are two samples that are independent of one another, or at least we suspect they might be because they're two different subject areas within mathematics. Right, you've taken both of these courses. You probably remember there being kind of a drastic difference between the way of thinking in algebra versus the way of thinking in geometry. So that's the purpose of this study. Teacher samples 25 students from their Algebra 1 roster and their geometry roster, and the scores are listed below. We have 90, 95, 99% confidence. We're looking for the difference in population mean test score, and we assume that the data comes from a distribution that's approximately normal. All right. So we're looking for whether or not there's a significant difference. And it's not clear based off the instructions whether these are the same 25 students from one year to the next. It's also possible that they're two completely different sets of students within the same school year, right? So, freshmen taking algebra and sophomores taking geometry. Right, so we'll go through the process. We're going to find the average of the items in the algebra column. Okay, lock it in, cancel that, equals average. I could just drag across, but I'll just do it like this. All right, we need the standard deviations, so equals sample standard deviation, first column. And like I said, I could just drag it across because A's will turn to B's. Oop. I said drag across. All right, so click on it and see that the row references are the same. The column reference changed from A to B. All right, difference in sample means. Apologies, I meant to highlight this as a place to report your answer. Right, so equals E4 minus F4. Now the standard error is a little bit of a different story. Right, this is a kind of an ugly formula. We know that there are 25 values in each column, so I can make a note that n is equal to 25. I'll do that here. All right, that's the number of items or people or whatever it is you're studying, right? And that's the same for each column, right? Not always going to be the same, so I'll make a little note here, pull these over, open it up a little bit, and reformat. And as is usually the case, these edits will be in place by the time you get to this activity. Right, so in each case, n is equal to 25. Right, you might not even want to put, if you want to actually reference these numbers, you might not even want to put the n equals. You might just put a 25 and then call that cell. But since we're only going to do that calculation once, I didn't think it really mattered. Right, and the numbers are right here, so we can just jump right to it. So equals, we're going to start with a square root. We're going to take this sample standard deviation, and we're going to square it and divide it by the number of elements in that column. So equals this squared divided by 25. All right, order of operations is going to take care of the exponent first, and then do the division. So then plus, I'm going to take this entry, square it, and divide by 25 also. If there are differing numbers of values in each column, then you would account for that here. So if there were only 10 values in this column, then this 25 would be a 10. All right. So we have our standard error. We have a difference in sample means. So alpha value, so 0.10. And the degrees of freedom, which is whatever the count value is minus 1. Right, so 25 minus 1 are just 24. All right, now the quirky thing about this is if there are two different values, we choose the smaller one typically. It's not 100% mathematically precise to do it that way. There is a formula for determining degrees of freedom between two independent samples, but by choosing the smaller of the two ends and subtracting one from that, you get something that's close enough, and in this case, close enough is good enough. So lock that in. Going from here to here to here, the only thing that's going to differ is the alpha value, so we might as well just take care of that right now. So 0.1 goes to 0.05. And then to 0.01. Lock them in. No need to update any row references because I actually just typed in the 25 minus 1. And again, you could just write 24 if you want. All right. So now for the low bound, I'm going to take the difference in sample means, so equals this, minus this times the standard error. I'm going to grab that. So at this point, now that we have all the information that precedes this part of the assignment or activity, it's really not very different from what you did with matched pairs. All right, so if you feel like you're doing the same thing a second time for a different activity, that's kind of normal because the process of finding a confidence interval is pretty much the same regardless of what type of confidence interval it is. It's just a question of what information you're drawing from. Right, so that distinguishes this from matched pairs, is that these are two independent samples. So the way we got our standard error, the way we got, well, the difference in sample means would be consistent, but the way we get the standard error differs. All right, and that's the main distinction. All right. All right, so we have our entire conclusion statement here. I highlighted group 1 is less than group 2 because both the bounds are negative. So now we move on to the 95% confidence interval. So I'm just going to grab my work from here. So F7, E11. E11 is pointing to this confidence level. T statistic is what I meant to say. All right, so I have that. Now let me pop this in here. And instead of E11, I'm going to make it E22. So now I have my low bound and I have my upper bound once I change the minus to a plus. So now, oh, well, actually not now. It's the same conclusion, right? The first group is going to be less than the second group because both of the bounds are negative. So let's try that over here with the 0.01. So we want it to point now to E33. And then minus goes to a plus. And now we have negative to positive, right? So negative low bound, positive upper bound. That's telling us that group 1 is equal to group 2. Really all that means is that we can't say that there's a significant difference between the two groups, right? Because 0 is in the middle of the set, not necessarily in the middle, sorry. It's in the set, which means that at 99% confidence, it could be the case that there's no difference between group 1 and group 2, right? But the other two confidence levels, they tell a different story. So this is not as conclusive as some of the other activities that you might have done. So we can say, I mean, you could reiterate one of these conclusions if you want, but I could also just, as a lay person, kind of speak it in the way I would say it to another person and say, most likely, the algebra scores on average are lower than the geometry scores. All right. because for 2 out of the 3 confidence intervals, 90% and 95, we showed that there was a significant increase from one to the other, right? And then for the 99%, we showed that there was no significant difference. So you can go in a bunch of different directions from here, but that's one of the things about confidence intervals that make it tricky, because you, using the same data, can draw multiple conclusions. So if you walked away from this being like, okay, so 99% confident that there is no difference, depending on what your agenda is, that might be what you choose to go with. All right, so you'll move on to the assignment here, which goes back to that online reaction test. And so you'll collect data between you and a partner that you're working with. All right, to make it independent, we would need to have 2 different individuals doing the activity together. All right, so yeah, there you go.